so 6:30 has to be the hard stop for the meeting. I'm sorry about that. And so I'll try to make this an hour or less, so Lisa will have enough time to talk. Will that work? Okay. Yeah. So this is the electronic Hamiltonian that we're interested in solving. Remember that this lowercase h is a one-electron operator. So this is the one-electron part of the Hamiltonian, which consists of the kinetic energy of the ith electron and then the attraction that the ith electron feels to all of the nuclei. And essentially, because the wave function doesn't treat any of the electrons differently, the one electron operator is going to be relatively easy to take care of, as hopefully you will see today. And then a review of what we talked about last time is that there's this abstract space of all n electron wave functions that are possible. Okay, and that is called the Hilbert space. Okay, the space of possible wave functions. And the Slater determinants are a subset of that space. So, so I kind of drew this picture, and there's some advantages, but also some limitations to this picture. So if this big square represents the Hilbert space of like all the n electron wave functions that are possible. Okay, the Slater determinants are a small subset of that space, which means that there are many n electron wave functions that are not single Slater determinants. Okay. However, your Slater determinants form a basis set that you can linearly combine to make any wave function that is in the Hilbert space. Okay. So if you've taken your linear algebra before, you can think of your basis vectors as like your x, y, and z unit vectors. Of course, the x, y, and z unit vectors by themselves cannot span the full three-dimensional space. However, you can take linear combinations of them and then reach any point within the space. Okay, so the Slater determinants you can think of as this as the basis vectors that span this much higher dimensional Hilbert space. Okay. Another set of wave functions to be aware of are the eigenfunctions or eigenstates of the Hamiltonian, and those are what we are interested in getting, right? Because they give us all of the properties of the system that we're interested in. And in general, because of this electron-electron repulsion term, the eigenstates of the Hamiltonian are not single Slater determinants. Okay, so they live elsewhere within this Hilbert space, but they could be accessed by taking linear combinations of Slater determinants, and that is called configuration interaction, which we will spend some time talking about before really diving into Hartree-Fock and showing you how it works. And even though this might seem a little bit backwards, I mean, after all, configuration interaction is a more advanced method than Hartree-Fock, but I think because I want to introduce this concept of this Hilbert space and n-electron wave functions, it's beneficial to talk about configuration interaction for like a week or two before we really spend a long time talking about Hartree-Fock. Okay, so there are two notes. The number of Slater determinants is equal to 2k2z. So this kind of scales factorially with k. So k is the number of atomic basis functions that you have, and if k is equal to your number of electrons, then what you have is called a minimal basis. Okay. Generally, when you want your calculations to be accurate, k is larger than n. Like, say k is equal to 10n will give you a medium-sized basis set. So 2k is, pretty much, well, 2k is always larger than n, and the number of Slater determinants in general goes factorially with the size of the system, right? And then, and because then these Slater determinants span the Hilbert space, and so do the eigenstates of the Hamiltonian. So there's the same number of eigenstates of the Hamiltonian. Okay, like, well, in principle, the Hamiltonian has infinite eigenstates, but because we're using a finite basis set, you can only get a finite number of eigenstates. So the number of the eigenstates is equal to the number of Slater determinants. Okay, so so even though you can imagine there being like a number of dots inside this box, the number of dots inside this box is equal to this the same number of x's, which are the eigenstates of the Hamiltonian. Okay, and then and both kinds of states, so the eigenstates of the Hamiltonian, they also form a basis that spans the Hilbert space, and so do the Slater determinants. Okay, so they span the same Hilbert space. You can think of this as being two different sets of basis vectors that span the same space. And in general, the eigenstates of an operator form an orthonormal basis of that Hilbert space. So these are just the two different kinds of two different kinds of orthonormal bases that we can talk about. Okay. So the eigenstates of the Hamiltonian, which we are generally interested in, and at the start of the problem we don't know what they are. You can write them as linear combinations of the Slater determinant, right? Because that is a property of an orthonormal basis, that you can form any other state in this Hilbert space by taking a linear combination. And we also have the condition that your states have to be normalized, which places a constraint on the linear combination coefficients. So if I use this capital phi naught, okay, to describe my the lowest energy eigenstate of the Hamiltonian. So if I find this ground state wave function, I've now come a great way in solving my problem, right? And in the case of full configuration interaction, which is which you can think of as the numerically exact solution of Schrödinger's equation, but is also not practical to do in most situations, you can think of this as being a linear combination of Slater determinants, starting from the ground state determinant, okay, and a graphical representation of a closed shell restricted ground state determinant might look something like this. So if you have 5 basis functions and 4 electrons, your ground state determinant might look like this. This might be the result of a Hartree-Fock calculation, for example. And then if you want to really span the full Hilbert space, you need to take all of the possible other Slater determinants that you can make with this same set of molecular orbitals. So the way to make other Slater determinants is to create excitations. Okay, so this is one possible excitation, right? Where I take one of the electrons and I remove it from one of the orbitals, occupied orbitals. Let's call it A, and let's call this one R here, and then now we are going to write out the my wave function as a linear combination of the Hartree-Fock ground state with and now this sum is going to run over all of the singly excited determinants. Okay, so these singly excited determinants, they are not necessarily good representations of the excited state, but they are still important basis functions for representing a wave function in the Hilbert space. And you can imagine there's already a lot of these, right? Because there are a lot of ways to take one electron out of an occupied orbital and put it into an unoccupied orbital. And a wave function is now this linear combination where the C's are to be determined, right? You can also go over the double excitation. So this is a sum over the A's and the R's that are possible. A double excitation might look something like this. This is an example where I've excited 2 electrons out of this orbital and placed them into this one. They can go into the same orbital or into different ones, as long as I don't have 2 electrons of the same spin in the same orbital, right? And now I have these linear combination coefficients A, B, R, S, psi AB, RS, where this represents my doubly excited determinant, and this represents the linear combination coefficient. And in this 4-electron system, I also have to write a sum over all of the triple excitations and all of the quadruple excitations, and then I've covered all of the Slater determinants that are possible, and this is my full CI wave function, right? And then if I can write down, and if I can write down this this huge matrix, the full CI matrix. For example, here would be psi AR H psi AR, and here might be psi naught H psi AR, and of course this is not a single row in the matrix, right? There's actually many rows represented by this because there are lots of different single excitations you can make, and if you write down the corresponding matrix elements for all the double excitations, all the triple excitations, and all the quadruple excitations, you now have your full CI matrix, which you can diagonalize to get the linear combination coefficients that gives you the ground state wave function. But because of the very large number of determinants that you can make, this is not something that we do in practice for most of our interesting problems. Okay, but this is conceptually helpful. Because we're going to now try to determine different kinds of different solutions of this, or different approximate solutions. Did you have something?
Yeah, there's one interesting I noticed that is here we are assuming the ground state is the Hartree-Fock solution, and in practice I found that even if the determinants are not actually the solution or just any random function formed by the basic set, the full CI result would be exactly the same, because the freedom of these coefficients is completely covering the upper coefficient.
That's correct. So and that's an interesting observation that when you're doing full CI and you are going over all of the possible determinants, it doesn't actually matter what sets of orbitals you choose to make your determinants. That you can they can do what is called a rotation or a unitary transformation of your orbitals, and your Slater determinants will still span the same Hilbert space. But if you are not doing full CI and you're only including a subset of the excitations, then the answer will depend on your choice of orbitals. And these orbitals will often come from Hartree-Fock, but they don't have to come from Hartree-Fock. There are other ways of generating orbitals as well. Yeah, so thanks for making that comment. I don't think I could derive that equivalence right now, but I'm sure there's a unitary transformation involved.
I think it doesn't actually need to be any Hartree-Fock results. I mean, when we're running full CI, we can just put the raw basic sets coefficients into there, and it's still giving us the result.
That's true. So the reason why I mentioned Hartree-Fock here is because Hartree-Fock will give us an ordering of orbitals in terms of energy, and then there will be, like a single lowest energy where you fill in the electrons, and then there's the concept of excitations from that, and that makes it easier to understand compared to, just saying that, oh, you can use any orbitals and fill them in any order you want.
Yeah.
That's generally true, but it's a little bit more abstract.
Yes.
Yeah. Okay. So I also want to note that that because your Slater determinants and your eigenstates of the Hamiltonian, these are just different sets of basis vectors that span the Hilbert space. You can also write a Slater determinant in terms of the eigenstates of the Hamiltonian, right? In principle, it's possible to do this. So I would write psi naught as a linear combination of some different coefficients d, and these would be and on the right hand side you would have the eigenstates of the Hamiltonian. So in principle, it's possible to do this. In practice, when would you ever do this? Well, these are the answers that we want, right? So you're never going to say know these and then take a linear combination of them to get some Slater determinant. But the fact that you could expand a Slater determinant in the basis of the eigenstates will prove useful in many of the derivations that we do. So, and in fact, we used something like this in order to figure out the variational principle, right? That Hartree-Fock is basically the variational minimization of the energy of a single determinant. So So in Hartree-Fock, you don't have a full CI matrix. All you really have is this single matrix element, but you have some degrees of freedom in the matrix of molecular orbital coefficients that you're tweaking. And you're basically tweaking the MO coefficients in order to make this single number as low as possible. Okay, so we'll talk a little bit about. I still won't give you the full formalism of Hartree-Fock today, but there will be some Hartree-Fock related concepts because I'll spend some time talking about the so-called minimal basis H2, which is the simplest possible multi-electron problem. Okay. Another thing that I want to mention before I start minimal basis H2 is that we're now basically equipped to do an initial computational project. Okay, so I've talked about how you could write your one electron problem. You can formulate that as a matrix where your matrix elements are formed of integrals, and then once you've formed your Hamiltonian matrix and your overlap matrix, you can actually solve this generalized eigenvalue problem to get your energy eigenvalues and your molecular orbital coefficients. This is called diagonalizing the core Hamiltonian. Okay, so and this is something that a lot of quantum chemistry codes actually do in order to give you an initial set of orbitals as input to Hartree-Fock, which tries to find the set of orbitals that minimizes the expectation value of the many electron energy, right? So, of these one electron orbitals, you can you're able to do without worrying about the repulsion between electrons because there's only one electron in this problem, right? And then and in order to build the H and the S matrices, you will have to construct integrals that look like this. And this is going to require some coding because phi I and phi j are atomic basis functions that are located at either the same point in space or different points in space. And then the one electron Hamiltonian is actually this Laplacian operator minus the attraction to a nucleus that can either be at the same location as your basis function or at a different location from your basis function. And once you write this, and once you do this project, you'll be able to actually solve Schrödinger's equation for molecules that contain one electron, right? Using and we're going to use the simplest basis functions possible, which are the S basis functions. That will make the integrals easier to do. The formulas are given in Szabo and Oslin, and what I'll do is I will do the problem myself first, and then I'll write the problem set. So I think most of you have taken at least one of my classes, and so I'll do the problem first. I'll write the problem set, and then I'll send it out. And you know, there's no grade for this, but it will be a great learning experience. And my hope is that by the time the summer starts, that at least we'll be able to share amongst ourselves a working code that can solve this one electron problem, and you'll be able to find some cool properties like the dissociation energy of H2 plus, right? You can't even do H2, but at least you can do H2 plus. Okay, so so now let's go to minimal basis H2, which is one step more difficult than this, right? Because there's now two electrons. So let's think about how to do that. So first, can somebody remind me, because I forgot, what is the minimal basis? Louder.
The definition or example?
What is the meaning of minimal basis?
The lowest number of coordinates orthogonal to describe the whole space.
The number of basis functions is as small as possible, right? And the smallest possible number of basis functions is what? Number of electrons. That's right. So for minimal basis H2, how many basis functions are there? There's two, because there's only two electrons. Right. So let's do that. we have a so here we have our here are the positions of my nuclei. Okay, and then and I'm going to have two basis functions. Okay, now you guys we are able to solve the Schrödinger's equation for the hydrogen atom, and by now I think the solutions of the hydrogen atom have at least been described to you, right? And the solutions of the hydrogen atom are these Slater functions, right? They look like exponentials that they decay exponentially away from the nucleus, and the fact that these are the exact solutions of Schrödinger's equation for the hydrogen atom means that they are pretty good basis that they are good basis functions that we could use to linearly combine to make our molecular orbitals. Okay, well, so let me draw what a Slater function looks like if I take this one-dimensional slice through it, and so this is actually all I'm going to say about Slater functions, because even though Slater functions are in a sense like more natural orbitals to use because they are the exact solutions of Schrödinger equation for the hydrogen atom, pretty much all of our calculations use Gaussian functions instead of Slater functions. Okay, that's because the product of two Gaussian functions centered in that don't have to be centered in the same place is actually just another Gaussian function, and we often have to deal with integrals where there are up to 4 Gaussian functions. So when you multiply them together and you decrease the overall number, that's a very helpful thing. So and usually the but at the same time a Gaussian function looks very different from a Slater function, right? A Gaussian function might look like this, and see, because it's a bell curve, it's much less sharp than the Slater function. And if I want to reproduce the Slater function in the sharp place, I have to draw this very sharp Gaussian, which doesn't have the tail of the Slater function, or I could make some kind of compromise in the middle, right? And in practice, what is done for the atomic basis functions is that a number of Gaussian functions are added together using a fixed set of linear combination coefficients to make a single basis function, and these coefficients do not change in the calculation. Okay, they are part of the basis set definition, and so the sum of the 3 Gaussians gives you something that is kind of Slater-like. And so the sum of these 3 white functions gives you this one yellow one, and this is the most commonly used minimal basis set, which is called STO3G. Okay, and the jargon is that we say this one basis function is a contraction of 3 primitive Gaussians. Okay, so each atomic orbital is a contraction of 3 primitive Gaussians. Okay, and then when you get to p orbitals and d orbitals, the Gaussians are also multiplied by spherical harmonics, but we're not going to worry about that right now. We're just going to worry about our s functions. Before we go any further, I wanted to catch myself because there's something that I said that was wrong. The number of basis functions in a minimal basis set is not always equal to the number of electrons, because if I have helium dimer, the minimal basis is also just 2 basis functions. So what is the more correct version of that statement? I don't actually know.
I usually count it as the smallest number of atomic orbitals add up, sum up the entire system. So like the hydrogen have one orbital that is the one that has
Yeah.
the other hydrogen have another orbital, so there are two orbitals. If you count the spin orbitals, there are four. And for like carbon, oxygen, and all the first row elements, they have 2s and 2p. So we at least have 5 orbitals for each of those atoms. So that's how I do it.
Okay, yeah, that's I think that's more correct than what I said. So for the STO3G basis set, you can think of every atom as possessing a different number of basis functions. For hydrogen, there's 1, and for helium, there's 1, and for lithium, because the 2s orbital is now occupied, you now have 2 orbitals for lithium, right? I think. Okay, I'm going to guess that there's 2 orbitals for lithium. Okay, but maybe there are 5 if you include the 2p orbitals. Okay, I'm guessing that there's 2, and for beryllium there's probably 2. For boron there are now 5, right? Because you're starting to occupy the 2p orbitals, and there are 3 of them. And for carbon there are 5, and all the way up to neon there are 5. Okay, so now let's we'll talk more about basis sets later, and now let's go back to this problem. So we have one atomic basis function on R1, and I'm going to call this phi 1 of R. Okay, so this is my first basis function. I also have another basis function. I'm going to draw it in a different color just so you know that it's a different function. And this is phi 2 of R, and it's made from the same combination of 3 Gaussians, but they are now centered on atom 2. Okay, so these are like the inputs of the calculation before I even solve for anything. That have these 2 atomic basis functions. Okay, in order to form my Slater determinant, remember that the Slater determinant is formed from these spin orbitals, which are combinations of spatial orbitals and the spatial part as well as the spin part, and you can also write it like this, where we have this determinant where you have orbital number 1 and orbital number 2, and in the top here you have electron 1 occupying orbital 1, electron 2 occupying orbital 2, and then here I have electron 1 occupying orbital 2 and electron 2 occupying orbital 1. Okay, so when we talk about minimal basis H2, we have this understanding that by the time we've solved the problem, we have some orbitals that are lower in energy than the other ones, and even though orbital energy is such an intuitive and obvious concept to us right now, just keep in mind that I haven't actually defined the orbital energy yet. Okay, but assuming that we have this concept of the orbital energy, one orbital is going to be lower in energy than the other one, and the ground state is going to have both electrons in that orbital, right? So this is the Slater determinant that I should end up with when I solve the problem for a minimal basis H2. And if I call this molecular orbital psi 1, like if I call the spatial parts of the orbitals psi 1 and psi 2, okay, then my first spin orbital, okay, my first spin orbital, which is a function of both my spatial and spin degrees of freedom, should equal psi 1 of R times alpha of omega, because this spin orbital is for the up electron, and then my second spin orbital is also going to have the same spatial part, but the spin wave function is going to have the electron pointing down. Okay, and just to remind us, alpha and beta are these objects where like omega is the spin degree of freedom. It can either be up or down. And for the alpha function, when I plug omega is equal to spin up into alpha, I get 1, and when I plug in spin down, I get 0, and vice versa for beta. Okay. I just remember when I took my upper division quantum class and the professor brought out these spin wave functions, it was very confusing. So that's why I'm mentioning it a few times. Like for how simple they are, they're often the most confusing part. Okay, so we also because these two spin orbitals are only different in their spin part, we have some alternative notation for them. This is another notation that we use, that we put this bar over the beta one. So you can either say psi 1. So psi 1 here implicitly includes the spin up part, and psi 1 bar includes the spin down part. Another way is to put alpha or beta as a superscript here. And I think I'm going to try to use the alpha and beta superscript more often, because in this case, you see here, you don't know whether this implicitly includes the spin part or not, so I'm going to try to use this alpha or
I
beta.
think sometimes we put the alpha and beta in parentheses because the superscript sometimes need to be used as excitations.
Okay.
Not here, but like replacing the R there, just like in the big parentheses on the right.
I've never seen that before.
Okay.
Yeah, I'm not sure I can do that on the fly right now, but maybe. Would it be okay if I left them like this? I'll just put the alpha and the beta here, because at least when we're using orbitals, like the concept of an excitation applies to a determinant and not necessarily an orbital. So the orbital index is always going to be down here. Okay. Okay, so I've talked about the Slater determinant now as being formed from these molecular orbitals, but there's a bit of a disconnect, because here I've told you about the atomic orbitals that go into the calculation. Right, so how do I form the molecular orbitals from the atomic orbitals? The answer is by taking a linear combination, right? And so my psi 1 atomic orbital is equal to C1 phi 1 plus C2 phi 2, where C1 and C2 are numbers that I need to determine by solving this, by solving the Hartree-Fock problem, right? The molecular orbitals form from the atomic orbitals. Yeah, sorry if I was wrong about that. And then this molecular orbital has to be normalized. Okay, which means that if I multiply it by itself and then I integrate, I have to get 1. Now the linear combination coefficients of your atomic basis functions are usually set up so that if you integrate the atomic orbital by itself, so if you multiply the atomic orbital by itself and integrate, you should get 1. Just keep in mind this is equivalent to an integrating the overall space of the complex conjugate times itself, right? That's what this notation here means. And same for phi 2 multiplied by itself. But atomic orbitals generally are not orthogonal to each other. Okay, and so there's this extra complicating factor that we need to worry about, that phi 1 and phi 2 actually have some overlap with each other. So phi 1 overlapping with phi 2, which is this same integral up here, except I have phi 2 instead of phi 1. Okay, I'm going to call this S12, which is the overlap integral between atomic orbitals 1 and 2. And in general, this is going to depend on the molecular geometry, right? If R is larger, then S12 is smaller because the orbitals are farther apart. So that means there's some condition on C1 and C2, right? So instead of there being 2 variables for me to determine, there's effectively there's only 1 variable. Okay, so I'm just going to give you the answer to the Hartree-Fock solution to this problem, because for minimal basis H2, you've effectively learned what the answer is in your general chemistry course, that the lower energy molecular orbital is just the symmetric linear combination of the two atomic orbitals, and that means C1 is equal to C2 in psi 1. Okay, so if C1 is equal to C2, then I can do this integral to find out what C1 is actually equal to, right? So this integral is equal to the integral over all space, and psi star is C1 star phi 1 star plus C2 star phi 2 star times C1 phi 1 plus C2 phi 2, okay? These are functions of R, right? The phi's are functions of R. And then this gives me integral over all space, the first term, so C1 star C1 phi 1 squared plus last two terms, C2 star, well, you see I could just write C1 squared, right? Plus, right, and because C2 is equal to C1, I can replace the 2's with 1's, so C1 squared phi 2 squared plus C1, and then now I have my cross terms, right? And so both of these are going to have C1 star C1, the inner and outer terms. So phi 1 star phi 2 plus phi 2 star phi 1. So there's actually 4 integrals for me to calculate. I can factor out an overall C1 squared. So this is equal to C1 squared. Okay, and the integral of phi 1 multiplied by itself, I can write it like this. Okay, plus same thing with phi 2. Okay, plus, and then here is phi 1, phi 2, and then plus phi 2, phi 1. Okay, and now we can plug in numbers because we know what these integrals are equal to. 1?
S1, 2.
Yeah.
S2, 1.
Right, and S12 is actually equal to S21. Okay, and that's because our atomic orbitals are real functions. Okay, so so this is equal to C1 squared 2 plus 2 S12, and this has to be equal to 1. So that allows me to solve for what C1 is equal to, and this is equal to 1 over the square root of 2 times 1 plus S12. Okay, and that's given me the molecular orbital of psi 1. Okay, and psi 2 is just the orbital that is orthogonal to this one, and I'm not going to solve for it because I want to go on. But this is equal to square root of 2 times 1 minus S12, okay, times phi 1 minus phi 2. So this is the so the psi 1 molecular orbital is now this function that I'm sure you guys have seen in general chemistry before. That if I take a slice through it, it looks like that. So there's some so electrons that occupy this orbital spend some of their time in between the nuclei, and then the other and the other linear combination kind of looks like this, and there's a nodal surface in between. And because we're using Gaussian functions, you can't have these. You can't really have the cusps at the nuclei. It's so these are kind of like rounded out because we're using these Gaussian basis functions, and that's what the molecular orbitals look like. Okay, And it should be a simple exercise to show that these are actually orthogonal to each other, and I won't spend too much time on that because there's still a lot of notes to get through. So any questions about this? Okay, so in minimal basis H2, you already know what the answer is, but generally you need to actually figure out what the MO coefficients are by minimizing the energy. And I haven't told you what the energy expression is, but it is this expectation value here. Okay, so so is the expectation value of the energy of a single Slater determinant. And for a long time I've talked about how you could evaluate these matrix elements between determinants, and Hartree-Fock just involves minimizing the energy of this one matrix element, right? This energy expectation value of a single determinant. In minimal basis H2, we already know what the molecular orbital coefficients are, so we don't have to actually do any minimization. But it's still very important to know what the energy is, right? I haven't told you what the total energy is, and that's what we're going to do now. So we know what the molecular orbitals are. Now let's figure out what the energy is. So yeah, let's do that. So expanding this, I have. Let me see what I can. I want to write out both. I want to write out both the spin orbital and the spatial orbital versions of this. So these are. So you see, chi1 and chi2, they both have the same spatial part, except chi1 can only hold an alpha electron, and chi2 can only hold a beta electron. And the Hamiltonian has the 1 electron part, plus the 2 electron part, plus the electron repulsion. A has the same Slater determinant on the right-hand side. Another way to write this is psi1 alpha, psi1 beta. Okay. So our job is to evaluate this quantity, and we're going to do it piece by piece. All right. So the first thing to note is that your Slater determinant treats all the electrons the same. Okay, that's because and that's because of a property of electrons that we know, that the electrons should be indistinguishable. So that means that we can that the expectation value of these two 1 electron operators are going to be equal. Okay, because all the electrons are treated the same. So so this, and in general, this so in general, the expectation value of like the sum of 1 electron operators is just going to be equal to the number of electrons times the 1 electron operator of just the first electron. Okay, so now you see this 1 electron operator operates on only the first electron. So we can now expand the Slater determinant to see how this actually works. So So expanding out the Slater determinant, we've got I'm first going to write out the left-hand side. So Slater determinant has 1 over square root of 2 for 2 electrons, and we have chi1 star of x1, chi2 of x2. Let me just write the Slater determinant up here for reference. Okay, so to evaluate the Slater determinant, you multiply this and then you subtract that, right? So chi1 star of x1, chi2 star of x2. That's because I'm writing the left-hand side minus chi2 star of x1, chi1 star of x2. Okay, so that's my first Slater determinant, and then I have my 1-electron operator, which remember just operates on the first electron, right? So I'll just write out the operator might as well. We have minus 1/2 times the Laplacian of electron 1 minus sum over all the nuclei in the system, and there's only 2 of them. Okay, so that's the 1-electron operator. You can see that it doesn't do anything to the second electron, right? So any function of x2 is going to pass right through this operator, and that's going to be really important. And then now I'm going to include now the ket part of the wave function. So chi1 of x1, chi2 of x2 minus chi2 of x1, chi1 of x2. Okay. So this actually belongs here, but now because there's 4 terms, it's easier for me to stack them like this, and then I can write out the individual terms. So what? Yeah. There's a 1 over square root of 2 thing. So there's 4 terms, right? So term A is going to have this, and then the operator, and then this. Term B is going to have this, and then the operator, and then this. And then I'm also going to have term C and term D that are the cross terms. Okay, and the important part of this is that this operator acts only on electron 1, so the functions of electron 2 pass right through it. So when I try to evaluate term A, okay, so for term A, let me try to do it. I'm just going to remember that there's this overall factor of 1/2 that I have to add onto the end. So term A looks like this, right? There's an integral or a sum over all the spatial and spin degrees of freedom of both electrons, and it's going to look like this: chi1 star x1 times my 1-electron Hamiltonian times chi1 of x1 times chi2 star of x2 times chi2 of x2. Okay, does that make sense? You see how the because the 1-electron operator acts on this orbital, this cannot pass through that, right? Because this acts on that, but because this operator doesn't act on the second electron, this becomes a separate integral. And now I can do this integral over the second electron, and what do I get? I just get 1. Yeah. So this so now this just becomes an integral over the first electron, chi1 star of x1, h1, chi1 of x1. Okay, and now going to introduce this notation here, where this one corresponds to spin. This is the spin orbital index. Okay, and this is called a one-electron integral. Okay, so that's a so this is the first of several kinds of integrals that I'm now gonna show you. So this is the so you've got your one-electron integral here, and I think we can only get through one-electron integrals today, and I'll come to two-electron integrals next time. So now I've evaluated one of the four terms in my expression, right? Now let's do term B. So for term B, I now have chi2 star of x1. So this is an integral over x1 and x2, right? So chi2 star of x1, one electron operator. So this also acts on only x1. Chi2 of x1, right? Times chi1 star of x2 times chi1 of x2. Okay, so that comes from these two terms here, and so you see this one electron operator operates on the first electron, so the functions involving the second electron pass right through it, and then now I can do this integral separately, and the answer is still the same, right? So and then I'm left with the integral over only the coordinates of electron 1, and then this becomes my other one electron integral. Okay, so now I have two different one electron integrals. One is over spin orbital 1, and the other is over spin orbital 2. In our case, the values of these two integrals will actually be the same, but I will show you that soon. Now for C and D, I'm not actually going to write them out, but you can see that if you can see the pattern that my one electron Hamiltonian only acts on electron 1. And that means I can do the integral over electron 2 separately, right? And here, if I look at this cross term, I now have chi2 of x2 and chi1 of x2, and these are different spin orbitals which are orthogonal to each other, either by virtue of the spins being different or being spatially orthogonal, right? And because I have different spin orbitals of my second electron, the C and D integrals actually cancel out. Okay, so what I end up with is just A plus B, which is equal to remember the overall factor of 1/2. So I have 1/2 1 H1 plus 2 H2. Right, that is the that's the expectation value of H1, but remember that we actually had two of these, right? We had H1 and H2, and they both evaluate to the same. So so when you evaluate the expectation value of H1 plus H2, the factor of 1/2 cancels out, and I just have a sum of these two one electron integrals. Okay, now I'm going to take 5 more minutes. I won't eat up here. I won't eat up too much of your time. So let me just write out this answer here. Okay, so this is the answer in terms of the spin orbitals. And then when I use these angle brackets, I'm leaving the answer in terms of spin orbitals. Now let's see what happens if I write out if I write everything out in terms of spatial orbitals, because remember chi1 is actually equal to psi1 alpha, and chi2 is equal to psi1 beta, right? And I think I only need to erase the bottom half of this board. Okay, all right. So this Slater determinant is equivalent to psi 1 of R1, alpha of omega 1, psi 2, or no, psi 1 of R2, right? Because it's the same spatial orbital, beta omega 2, and then psi 2 R1, beta omega 1, and then psi 1 of R2, alpha omega 2. So on the top I have the same orbital, right, and on the left column I have the same electron. So now let's try to evaluate this Slater determinant, and this is going to be the last thing I do today. So on the left-hand side I have psi 1 star of R1. Well, let's see. So first I have so remember that this is an integral. This is an integral over the coordinates of electron 1 and electron 2, as well as a sum over the spin coordinates of electron 1 and electron 2. Right. So this is the same as writing integral over x1 and x2, because x has the position and the spin degrees of freedom all contained in there. And then so first my first Slater determinant, I've got 1 over square root of 2 times psi 1 star of R1, alpha star omega 1, psi 1 star of R2, beta star of omega 2, okay, minus psi 2 star of R1, beta star of omega 1, psi 1 star of R2, alpha star omega 2, okay, and then my one electron operator, and remember that the one electron operator doesn't actually care about the spin degree of freedom. The one electron operator acts on the spatial coordinates only, so this minus 1/2 times the Laplacian, which is the derivative with respect to spatial coordinates, minus the attraction to all of the nuclei, right? So that means the spin wave functions will be able to pass right through this this one electron operator. And now let me write the non-complex conjugate version of this. So try to write faster. And just copying this line, but without the stars, right? And I made mistakes here. There is no psi 2. They're all in psi 1 because both electrons are occupying the same spatial orbital. So there's no 2 here. These are all psi 1s. Okay. Let me erase the top half of the board now because I'm going to try to evaluate this integral. And even though it looks complicated, the answer is actually pretty simple. When you write things in terms of spatial orbitals. Okay, so first let me write out the 4 terms. You have A and B and C and D. Okay, and we can take care of C and D first because they're easier. I said that this Hamiltonian doesn't act on the spin degree of freedom, right? That means that alpha of omega 1 can pass right through this operator and multiply directly with beta star of omega 1. So I have alpha times beta of the same spin degree of freedom. That's going to give me 0 overall. Okay, so that means C and D are both going to be 0. Okay, and then the spin degree of freedom can pass through that Hamiltonian operator and multiply with each other. So I have alpha star alpha And when I take the sum over omega 1 of alpha star alpha, I just get 1. Same thing happens with omega 2 beta star beta, and here I have beta star beta and alpha star alpha. So after doing the sum over all of the spins, I just get factors of 1 for part A and part B. Okay, so let's so for part A, I have this overall factor of 1/2 out front, and then the sum over the alpha and beta just give me 1. So now I have integral over R1 and R2. Okay, psi 1 star R1 H1. Psi 1 star of R1, and then I have psi 1 star of R2, psi 1 of R2. And you see this is actually a product of two separate integrals, and the integral over the coordinates of electron 2 is thus equal to 1. So I end up with a single integral that is left, so D3 R1, psi 1 star of R1 H1 psi 1 of R1, and when I use these curved parentheses around my, like to denote my integral, this is a 1 electron integral, but it is now in terms of spatial orbitals. Okay, and remember what we had before was this integral in terms of the spin orbitals, right? So, and so spin orbital 1 is actually equal to spatial orbital 1 times the alpha spin wave function, and these two are actually equal to each other. Now let's do the B part. So doing the B part, I have 1/2 same integral, and so here you still have electron 1 occupying psi 1, right? So psi 1 star R1 H1 psi 1 star R1 psi 1 star R2 psi 1 R2. So when I write this in terms of spatial orbitals, the B integral and the A integral are actually exactly the same. And yeah.
The side one, side of H don't have stars on it.
Yeah. Thank you. There's no star here.
No, side 1 R2 has this one.
The R2 one.
Oh, right.
Yeah.
Right. This one.
Yeah.
Yeah. Thank you. Okay. Yeah. Thanks. Okay. So you can see that this 1 electron integral in terms of the spatial orbitals is actually the exact same as this term here. But when I wrote it in terms of the spin orbitals, it was 2H2. So what happened? What happened is your second spatial orbital is really equal to my first. Well, my second spin orbital is really equal to my first spatial orbital times beta, and my first spin orbital was equal to that same spatial orbital times alpha. So the indexing of my spin orbitals is different from the indexing of my spatial orbitals, and so the final expression of the 1 electron part of the energy depends on whether you're using your spin orbitals or your spatial orbitals, but they evaluate to the same number. Okay, so the final answer that I'll write up here is the 1 electron part of the energy. And this is equivalent to writing the same thing in terms of the spatial orbitals. So and now going back full circle. Remember that this is what we ultimately wanted to do, right? Because this is the Hartree-Fock energy of my minimal basis H2. So we've now done this part, but we don't know what this part is. This is the 2-electron part, and that's what we're going to talk about next time. Okay. And it's 5:20, which means you have about an hour. Thanks. Yeah. Do you want to be recorded?
Up to you.
I don't think it's necessary, but
I can do that.
okay. I don't know how to stop